Our next speaker is Professor Efrat Shimron. Efrat is the assistant professor at the Technion with dual affiliation at the departments of electrical and computer engineering and biomedical engineering. She was previously a postdoctoral fellow at UC Berkeley. Research spans the development of compressed sensing and AI algorithms for medical imaging, focusing on MRI. She also investigates topics of bias in AI models. Efrat recently received several career awards, including MIT's Rising Star in Electrical Engineering and Computer Science Award. Efrat will talk about data crimes, the risk in naive training of medical AI algorithms.
Hi, everyone. It's working? Okay. Thank you, Chen, for the wonderful introduction. And I'm really excited to be here. It's great to be back in Israel. And so without further ado, let's start going forward. I just want to mention I really enjoyed Amit's talk. Amit talked about this perfect world where there's tons of data and you can train models that are almost as great as our brains. I'm going to show you the opposite. So let me know which one you think is more realistic at the end. I'm going to show you what happens when things go wrong and you don't have enough data. Okay, so just a little bit of background. I recently spent 3 years in the San Francisco Bay Area. This is actually a real image. I think it was not generated by ChatGPT, but it could be improved with ChatGPT. And I did my postdoc at UC Berkeley and Stanford. That was wonderful. And I recently moved back to Israel, which is great to be back. Of course, it's not a wonderful year, but we all hope for the best. And now I'm opening my lab at the Technion. So, in computer vision, as you all know, images are taken with cameras, but that is not the case in medical imaging. When we want to see into the human body, then we need to transmit some source of energy or some waveform into the body, and then we detect a signal on the other side, because we can't just take photos, obviously. And so now, once that we have the measurements of the detector, we need to generate images from them. And my research field focuses on those algorithms, image reconstruction algorithms that generate images from the measurements. And specifically, I work on MRI. MRI is a really fantastic, amazing modality. Let me show you why. MRI is safe. It includes no ionizing radiation at all. It offers rich visual information, and it captures both static and dynamic details of the human body, as you can see here in these videos. I hope you see my marker. So on the right-hand side on the top, you can see a video of a human child. This is a scan from Stanford Children's Hospital. In the top down in the middle, you can see an embryo. This is a scan of a pregnant mother. And you can also see blood flow through the veins. You can see an abdomen, a leg, and so on. So really, this is a fantastic modality. Look how rich the information is that we can capture with it. However, MRI also has some limitations. First is the long scan duration. It usually takes 30 to 60 minutes to scan one person. This creates sensitivity to motion artifacts. As we all know, taking images of moving objects results in blurring, and the same thing happens in MRI. People breathe during the scan, they move, the system samples the data very slowly, and so we get motion artifacts. And of course, this is a problem, especially for children, where they tend to move a lot, and so sometimes we need to administer anesthesia for them, and that carries risks. On top of that, MRI is very expensive. A single scan can cost up to $1,000. And so even though it's a fantastic modality, it's not really widely accessible to large populations. My research aims to change all of that and to make this amazing system accessible and affordable so that all of us will be able to enjoy it and we won't need to wait months and months for an appointment. So how can we make MRI scans faster? In order to explain that, let me show you a little bit of the background of how the system works, just a very little bit. So in MRI, we take measurements in the Fourier domain, which is known as K-space, and this is done in a pixel-by-pixel manner. So unlike computer vision, where we take a camera, we take a photo of all the pixels simultaneously, here we need to sample the data sequentially. And the system works very slowly. However, if we sample enough data, using a rate that follows the Nyquist rate, then we can reconstruct images using the inverse Fourier transform. That's straightforward. But as I said, this is very slow, and it can take almost 1 hour to scan one person with this. So if we want to accelerate scans, a common approach is to undersample the data, which means that we collect only some pixels, as you can see here. Now, that's fast, right? But now you can no longer use the inverse Fourier transform, because here we violate the Shannon-Nyquist sampling theorem. And so what we really need are image reconstruction algorithms that enable us to infer accurate images from limited samples of data. This is a highly ill-posed inverse problem, and we need optimization techniques to solve it. And so my research work focuses on developing those reconstruction algorithms. Of course, this is a field of active research because MRI has been around for many years now, and many, many techniques have been developed over the last few decades. And of course, if not surprising to you, will be that today we're seeing machine learning methods that are giving state-of-the-art results in this field. However, if you want to train your own reconstruction algorithm, let's say that you're excited about this field, you really want to do some good work and to contribute to the medical imaging world, you want to develop your own algorithm. Very quickly, you will run into a challenge. The challenge is, where do I get my training data from? I mean, I just told you, MRI scans are super long and super expensive. We don't have data sets of millions of images because it's impossible to acquire them. So what do? You have this fantastic idea, you want to train your model, no data. What do? That's a real problem. And so what I noticed is that when people run into this obstacle of lack of data, they try to come up with all kinds of creative solutions. And so they aim to do a good job, but sometimes when they think of creative solutions, they actually, they get results that may look good, but are actually false. And so I realized, and also we discussed it a lot at Berkeley, we realized that many papers are coming out with biased results, with results that are too good to be true, and I'll show you why in a minute. And so in order to raise awareness to this growing phenomenon, I did this research, which is titled Data Crimes. So now let me show you what are these crimes. So in order to describe these crimes, I'm going to show you a standard research pipeline, which is, this is a methodology that is commonly taken in our field, and you will find many papers, dozens of papers that are based on this pipeline. So if you want to develop your reconstruction algorithm, what you would do is to start with fully sampled case-based data. Then you will undersample the data retrospectively. This is done after the scan on your computer. Then you run your algorithm. It can be any algorithm, a new one or an existing one, and you get a reconstructed image. Now, in order to prove that your algorithm is doing a good job in producing an accurate image, you need to compare it with something, right? This is medical imaging. We have to achieve accurate results. So what is usually done is to compare it with the gold standard image, which is obtained from the fully sampled case-based data. And the comparison is done using error metrics such as NRMSE, normalized root mean square error, or structural similarity, and so on. So as you can see, this entire research pipeline, which is super common and basic, actually relies on the existence of fully sampled case-based data. Now, back in the days of linear techniques and compressed sensing, 1 or 2 or 3 examples were enough. But now that we want to train deep learning models, we don't have enough data. So what do? How do you develop your reconstruction algorithm when there's no data? So what do people do when they want to find data? What would you do? The first thing that you do is you would go to Google, right? You go online, you write MRI data, you got tons of results. Try me, you can check me very easily. And then you choose one of them and you download the database. Okay, here's some data. And if you look at those data sets, you will see that those databases offer MR images. Not case-based data, but images. But you need case-based data, right? So what's a very simple solution? To apply the forward Fourier transform and synthesize case-based. There is case-based. Now we can do the research. Now we can train reconstruction algorithms, right? Not exactly. What's the problem with this pipeline? And this is a naive approach to development of deep learning algorithms. The problem is that MR images that are found in online data sets are often preprocessed, and they're preprocessed by hidden data preprocessing pipelines. Those pipelines, let me tell you, are black boxes. Nobody knows what's going on inside them. The details most commonly are not reported on the website of the database or on the journal, nothing. You can't find them. And if you can't find those details, it's very easy to ignore them. Like, who cares? It was done a few years ago by somebody else. I'm just developing my algorithm. And so people take those data sets and use them for developing reconstruction algorithm. But what's the problem? Those data sets do not contain raw case-based data. Because if you try and check Google MRI data, you will see that there are many results. Some data sets, the ones on the left, do offer low k-space data, but those are very few, only a handful of them. Many other data sets offer preprocessed data. Those, the ones here on the right, were prepared for downstream tasks. Let's say for Kaggle competitions that include tasks such as segmentation, tumor classification, biomarker extraction, and so on. For downstream tasks, it's okay to preprocess the data because those tasks begin from a reconstructed image. But the problem begins when somebody takes those data sets that were already preprocessed and uses them for synthesizing k-space data and developing reconstruction algorithms. Why is that problematic? Because the preprocessing steps actually reduce the dimensionality of the data. They change it. Those steps include things like JPEG compression, coil dimension reduction, zero padding, which means cropping k-space or enlarging k-space artificially, and so on. But because those details are not reported anywhere, it's very easy to ignore them. What I found out is that those small details that we tend to ignore actually have a huge influence on the results of the reconstruction algorithms, and they lead to biased results. But you know what? The results are not just biased. Surprisingly, they're fantastic. They're really good looking. You can try me. Google MRI data, download any database, run your favorite reconstruction algorithm, you will get beautiful results. Why? Because the inverse problem was made easier to solve because of the data preprocessing pipelines. However, many people are newcomers to the field. You know, sometimes they're students, they're getting excited, they don't really know, and they also don't really care. And so what do people do when they get fantastic results? What do we do in academia? We publish. Thank you, Chaim. Of course, so we publish. So it's very exciting. We get wonderful results. We go, we write up the paper very quickly, we submit. Many times people miss the fact, completely miss it, that the data was preprocessed and the results were biased, and you know what? Reviewers also miss it. And so those papers are getting published. And so what I noticed is that a lot of papers are coming out with biased results simply because there's no data in the field. And so in order to raise awareness to this phenomenon, I did this research where I wanted to demonstrate how this happens. I said, I'll do the crimes myself, and I'll show. We can show it statistically. Let's see what happens. And so what I did was to take one of the few data sets that do offer low k-space data, and then I preprocessed the data myself, and I trained and tested 3 super well-known algorithms. Each one of those, that I'll show you soon, have thousands of citations. So these are canonical algorithms in the field. What you see here in this graph, on the y-axis, you see the error metric, the normalized root mean square error, and on the x-axis, you see the level of the preprocessing. So left is the original data, and right is highly preprocessed data. And without going into all the details, you will find them in my paper, you will see that the experiments show the same thing. The more the data is preprocessed, the better the results become. Surprise. Okay. So what you say is that the algorithm does better and better as the data is more processed, because the inverse problem is made easier to solve. So here's one algorithm. Let's see another one. You see this, the same results, and you see this, the same results. 3 different algorithms, super well known. So what we see here is that when you train and test your algorithm on processed data, you can get results that are up to 30% better or 40% better. You see this? 38%. And people go and publish that. And they will say that this improvement has been obtained due to a new architecture or a loss function or, you know, a vision transformer or an attention layer or something like that. Well, in fact, the improvement may have been obtained only because this new paper reported results for processed data, while a previous paper reported the results for original k-space data. And so I encourage you to be very careful when you do your research and when you find data and you plan your research methodology. Check the details very carefully and ask yourself, am I using the data correctly? Was the data designed for this task, or was it used for another task and I'm using it in a wrong way? And also when you act as reviewers, ask yourself, did the authors of the paper that I'm reviewing, did they design their research correctly? Is this a true result or is it biased results? Because you see what happens. And still many papers are coming out with such biased results. And so I published this work 2 years ago, and it was published in the PNAS, in the Journal of the Proceedings of the National Academy of Sciences in the US. And the community really got excited about it because they understood that it's a real problem in our field. And people started asking me a lot of questions. And one of the questions that I got many times was, well, you know, they said, you know, Efrat, let's say I have no data because I can't sample. What if I can only find processed data, I download it, and I train my algorithm on that? Can I now use my algorithm in the hospital? Will it do okay? Will it do well for patients? So then I became interested in this question. Can we use algorithms that were trained on processed data and applied them for clinical data. And so I did this research where I took one of those models that were trained on processed data, and now I tested it twice on processed and non-processed data. And so what you see here is an image of a knee. This one contains a pathology. This person, unfortunately, has a torn meniscus. And what you can see on the middle column is that the result for the processed data is very sharp. I hope you see it. There are details that indicate a torn meniscus. But when the same algorithm was now tested on the raw version of the same data, the algorithm failed. The results are blurred, and the torn meniscus is gone. So the clinical diagnosis might be wrong in this case, only because the model now exhibits it has to face a distribution shift between the training and test data. So it's not a good idea to do this. So in summary, what I showed in this research is that naive use of big data could lead to biased results. I also showed something else. I showed that error metrics are blind to the preprocessing. Why? Because those metrics measure the difference between the reconstructed image and the so-called gold standard image, but it isn't really the gold standard. It's based on the same synthesized case-based data. So the metrics are completely blind to the bias, and they cannot be trusted in this scenario. So again, I encourage you to think very carefully about the papers that you read and also the research that you plan. And ask yourself, can I compute this, and what's the meaning of computing this error metric? And I also showed that algorithms that were trained on processed data could fail for clinical data, and they could miss clinically important details, and of course, we don't want that to happen. So, what do you do? What do you do if you want to develop your new deep learning or AI reconstruction algorithm? You have this great idea for a great architecture, and then you're really excited about this research, but you just can't find data. And I remind you, the acquisition is too slow, so it's impossible. In many applications, especially body imaging in pediatric patients, which is what you see here, it's impossible to get fully sampled data. Simply, the machine is too slow for that. So how can you develop your reconstruction algorithms? So what I show you next is a framework that I'm developing with my students that addresses this challenge. And here we combine techniques for fast sampling and self-supervised reconstruction without any fully sampled data. So this work was led by two of my students at Berkeley, Han Chi and Fred Wang, and we're continuing it at the Technion. So let's say that you want to develop dynamic volumetric reconstruction algorithms. So this is a 3D plus time or a 4D problem. Ideally, what you want to do is to acquire all of K-space again and again over time, but there's simply not enough time for that. What we propose is to sample only one K-space band at a time, only a narrow stripe of K-space. That's fast, right? But it gives data with a limited resolution because we limited the extent of the sampling in K-space in one dimension. The question is, can we use this data? What we propose is to split the training process. If you think about how we train neural networks, we use algorithms such as stochastic gradient descent. And those algorithms usually take one example at a time. We propose to break it into small parts and acquire those small parts of the data from different subjects, because now we can comply with the sampling requirements. And so let's say that I scan this child at the hospital, and now here comes another child, and I will scan a different band in K-space. That's possible. And here comes a third child, and I will collect a different band in K-space. All the data will be blurred because it has limited resolution. Can we use this limited resolution data and train models that will give high-resolution reconstructions during inference? Can we do that? The answer is yes, and this is the method that we're developing. So we propose a self-supervised technique. In addition to the acquisition method, which I just showed you, we propose to take every one of those bands and to sample it retrospectively, train an unrolled neural network. I won't go into all the details. You can find them in our paper. And then we use the band for supervision. But the important thing is that we rotate the band angle. We choose the angle randomly from a uniform distribution. And so if we have enough subjects, enough examples, we will eventually cover all of K-space, and the network during the training iterations will be exposed to all of K-space. So it can learn all the areas, even though it didn't get even one single fully sampled example. And so to do that, we introduce an algorithm called stochastic gradient descent over K-space subsets. Again, all the details are in the paper. We proved it mathematically, and we showed that it converges. And we also introduce a loss weighting mask, because if you think about it, all the bands contain the center of k-space, so there is risk that the network might develop bias towards accurate estimation of the center, because then on average it will always be correct. But we want the network to do the opposite. We want it to learn the periphery of k-space, because that's where the high-frequency details are. That's where those subtle, small details, important details are located. And so we introduced this loss-weighting function or mask, which inhibits the loss in the center and places more emphasis on the periphery. And what this does is to enforce the network to learn the periphery from those few examples that it actually gets. So that was the training. For testing the network, we do something else. We acquire data from the entire k-space, but with an undersampling mask, and then we do inference on the pre-trained network without any further training. And we show, both analytically and numerically, that the network can reconstruct high-resolution images even though it did not see even one such image during training. This is achieved due to the combination of our unique sampling process and training optimization process, which I just showed you. So to summarize, what we introduced is a method for training on partial limited resolution data, which achieves test time generalization to high-resolution reconstructions. And there's many more experiments and results in the paper. So let me take the very last minute to tell you about another research direction in our lab. As I told you in the beginning, MRI systems are super expensive, but now we're seeing the emergence of a new generation of MRI scanners called low-field scanners. Those are small, portable, and very cheap, 10 times or 20 times cheaper than the clinical systems. They became FDA cleared a couple of years ago, and so it's a really exciting new technology. But the problem is that they operate at a very low magnetic field, so they suffer from low signal to noise ratio, and also the scan time is very long because we need to repeat the scans many times to increase the SNR. And so we are developing, together with my colleague, Professor Matt Rosen at Harvard, we are developing AI methods for speeding up the acquisitions and also improving SNR. And so with that, I would like to conclude and acknowledge all the wonderful people that I'm working with, as well as my students in Berkeley and at the Technion. I also want to mention that we have some open positions for masters, PhD, and postdocs. So who knows, the next person here could be you. If you're interested, check out our lab website, and thank you very much.